Okay, now some chemistry here, doping. I think Robert was saying this earlier when I asked what are the electron control devices. The reason the electron control devices are able to, make a smart decision is because the fact that we do this process, it's referred to as doping. Okay, doping, you can think of it, I don't know, a good analogy would be, you have these athletes, they take all these immune boosters and strength boosters and steroids and all that to improve their uh, performance and things like that. Not steroid, but we have seen people caught taking steroids, but then they are fine and all that. But there are some uh, things available that they use to uh, strengthen up their muscles and increase their productivity. Doping is a kind of a same thing. Okay, so you take one element, okay, you uh, you take another element, and you take the two good things of the two elements and then mix them together to make a hybrid material, which has both important characteristics of the two materials. So, okay, so in a simple word, that's what doping is here. The electric characteristics of silicon and germanium are improved by adding materials in a process called doping. Okay, there are two kinds of dope materials. One is the N-type material, and the other one is the P-type material. So this N-type material is associated with the excess of electrons. Okay, excess of electrons. And then this P-type means the excess of holes. Okay, now before I move, I also want to explain you what is the difference between electrons and holes. Now, in the valence band, okay, in the valence band, you had a lot of electrons here, correct? A lot of electrons like this, okay? When some band gap energy, and say this has some band gap energy of 1 electron volt, okay? When the band gap energy level is applied at the valence band, say 1.1, these electrons will eject and will move to the conduction band, right? Conduction band CB. Okay. When this electron here move over here, it will leave a hole. It will leave a hole. Okay, and hole carry positive charge. Similarly, when this electron moves here, this will become a hole. Okay, so the absence of electron is basically hole. Holes are positively charged. Okay, holes are positively charged, and then electrons are negatively charged. Okay, holes and electrons, they both can take part in conduction. Okay, they both can take part in conduction. Take part in conduction. Okay, one of the advantage of electron is they have higher mobility. Okay, so if you have a point A and point B, okay, electrons will move faster. Okay, they have higher mobility. They have at least 2.5 times more mobility than those of the holes. Okay, so N-type materials are very popular and in high demand. Okay, because they have the higher mobility. Okay, so N-type material contains an excess of conduction band electrons. I just told you guys that. And P-type material contain an excess of the valence band holes. So it should be clear going from here, what are the electrons and holes. Now, talking of P-N junction, okay, so we are getting into the construction of the device, how a diode is made, what goes inside, okay? So on the end of a silicon or germanium crystal can be doped as a P-type material and the other end as a N-type material. Okay, this results is a P-N junction. Okay, so say you can have these both material P and N here. Okay, these both can be silicon. Okay. These, I can just write Si here, and these both could be silicon. Okay, if I doped this silicon, okay, with an element that has, you know, more holes, more positive electron, then this would make a p-type material. Okay, if I take a material which is silicon and then dope it, basically mix it with you know, a material which has extra electrons, then I would have extra electrons in this region, extra electrons, right, like this, and it would make a n-type material. So this is what it means. So think of it, there is some element, okay, okay, and it has some number of electrons, okay, okay. To this electron, to this element, I add impurities, adding impurities. Okay, if I want to make this material an n-type material, by adding impurities would mean I would add more electrons, more electrons. So n-type material would mean it has more number of electrons and less number of holes. Plus is holes, negative is the electrons. So if you see all the electrons which are negative charge in red and orange, these are electrons, and you have tiny number of holes. This is important to do this to make these materials n-type and p-type, because that is when we make up these devices, diodes. And similarly, if you look at this silicon, which is an n-type, so this was the n-type material, right? Similarly, if I have a p-type material, say I have a p-type material which got a lot of holes in there, okay, and some electrons too. Okay, initially the number of electrons and number of holes are going to be same, but when we add impurities, then the number of holes will increase. So plus, 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 things like that. Okay, so I have made it, essentially made this a P. And if this was silicon, so this is the N-type, so this is a P-type silicon, and this is a N-type silicon. Okay, all right, so this is the basic construction. We don't have to worry about it at this point, how this adding impurity process is done, because this is something that you will learn in a course called Semiconductor Materials and Devices. Okay, all right. Now let's learn about the PN junction here. So again, think of this block, which is the diode right here. Okay, this diode right here. Okay, now what have we done? This is the p-type material on the left, okay, which is the gray region. The blue region that you see on the right is the n-type material. Okay, now in a p-type material, what are the majority carriers? Holes or electrons? Yes, folks.
P-type is holes and the N-type is electrons.
Correct, awesome. So majority carriers here are holes, okay, and then majority carriers in an n-type material are electrons. Okay, so I have holes here, a lot of holes, a lot of holes, a lot of holes here, okay, a lot of holes in red, okay, and I have a lot of electrons here in blue on the right, okay. When I combine these two materials, which is the p-type material and the n-type material, P having majority carriers as holes and N having electrons as a majority carriers, keeping in mind what we learned from week 1, there's electrostatic force that exists between the oppositely charged materials. Positive is attracted toward negative, negative charged particle is attracted towards the positive. So when I combine the two materials which have two majority carriers, they both are different. One is positive, one is negative. What is going to happen? Yes, folks.
The negative charges are going to move towards the holes.
Yes. So positive charges over here will be attracted towards here, and the negative charges here will be attracted toward the positive charges over here. And that's where you see this negative charge barrier over here. negative charge barrier over here. And similarly, you see the positive charge barrier over here. Okay, a very simple phenomena. Okay, now I may ask you a question. Okay, so we understand this negative is attracted toward this positive, and this positive here is attracted toward this negative. Then why this electron is moving to over here? Why this electron is not moving over here? Why is that? So what is happening is when these electrons migrate from one material to another material, okay, they make this depletion region right here, this depletion region, okay? You think of it as a resistance, okay? When this depletion region broadens up, okay, so right now it's pretty big, okay? When the resistance increases, will the current flow? Or you have a nucleus here, and then you have the electrons over here, and then you have another, say, electrons over here. So this is the farthest one from the nucleus, right? This will be attracted here, but this might not be attracted because it's far away. Similarly, this electron over here that I encircle is far away from this positive. So there's no force of attraction between them. Or if there is any force, it's very weak, not enough to move this electron to go over here. So that depends upon the depletion region width, okay? The higher this width, the higher resistance, okay? All right, we call this a PN junction, okay? We call this a PN junction. And PN junction, I can draw a line here. It's basically when the P-type material and N-type material combines, okay? You see this purple line? That's the PN junction here, okay? When the P-type material combines with N-type material, that's where we call it a PN junction. And around that region, PN junction, we see this depletion region that builds up because of the electrostatic phenomena. So what have we learned here? At the PN junction, the excess conduction band electrons on the N-type side are attracted to the valence band holes on the P-type side. Okay, understood? The electrons in the N-type, okay, material migrate across the junction to the P-type material. Perfect, we got that too. The electron migration results in a negative charge on the P-type material, which is this one right here, correct? And then a positive charge on the N-type side of the region, which is this right here, okay, understood. The result of the formation of a depletion region around the junction. So this is your junction in purple, and then you have this this depletion region, which again depends upon the how many electrons are able to migrate to the other. So the higher the depletion region, it acts as higher resistance, and therefore there will be less electron flow now, okay? When this depletion region decreases, so when, say, you know, maybe I could say that right now the depletion region is this big, right? It's this big. If I change it to something like this, what would happen to the resistance? Will it go up or will it go down? Depletion region is acting as a kind of a resistance for us over here, okay? So if the depletion region becomes smaller, like I'm saying here, the resistance is gonna go down. Now, the trick here is the way we get these resistance to change is by applying an external voltage, okay? By applying an external voltage to the terminals of the diode. By doing that, we can control the width of this depletion region.